Learning objectives. In this chapter, the user will learn the following in detail. Representation of solids, primitive instancing, sweep representations, boundary representations, spatial partitioning representations, constructive solid geometry methods, octrees, binary space partitioning trees. Binary space partitioning trees. Binary space partitioning (BSP) trees recursively divide space into pairs of subspaces, each separated by a plane of arbitrary orientation and position. The binary tree data structure created was originally used in determining visible surfaces in graphics. Each internal node of the BSP tree is associated with a plane and has two child pointers, one for each side of the plane. Assuming that normals point out of an object, the left child is behind or inside the plane, whereas the right child is in front of or outside the plane. If the half space on a side of the plane is subdivided further, then its child is the root of a subtree. If the half space is homogeneous, then its child is a leaf representing a region either entirely inside or entirely outside the polyhedron. These homogeneous regions are called in cells and out cells. To account for the limited numerical precision with which operations are performed, each node also has a thickness associated with its plane. Any point lying within this tolerance of the plane is considered to be on the plane. The subdivision concept behind BSP tree is dimension independent. Thus, part A of this figure shows a concave polygon in 2D bordered by black lines. In cells are shaded light gray, and the lines defining half spaces are shown in dark gray, with normals pointing to the outside. The corresponding BSP tree is shown in this figure in part B. In 2D, the in and out regions form a convex polygonal tessellation of the plane. In 3D, the in and out regions form a convex polyhedral tessellation of 3 space. Thus, a BSP tree can represent an arbitrary concave solid with holes as a union of convex in regions. An arbitrary BSP tree does not necessarily represent a bounded solid. For example, the 3D BSP tree consisting of a single internal node with in and out nodes as children defines an object that is half space bounded by only one plane. Consider the task of determining whether a point lies inside, outside, or on a solid, a problem known as point classification. A BSP tree may be used to classify a point by filtering that point down the tree, beginning at the root. At each node, the point is substituted into the node's plane equation and is passed recursively to the left child if it lies behind, inside the plane, or to the right child if it lies in front of, outside the plane. If the node is a leaf, then the point is given the leaf's values, either out or in. If the point lies on a node's plane, then it is passed to both children and the classifications are compared. If they are the same, then the point receives that value. If they are different, then the point lies on the boundary between out and in regions and is classified as on. This approach can be extended to classify lines and polygons. Unlike a point, however, a line or polygon may lie partially on both sides of a plane. Therefore, at each node whose plane intersects the line or polygon must be divided, clipped into those parts that are in front of, in the back of, or on the plane, and the parts classified separately. Thibault and Naylor describe algorithms for building a BSP tree from BREP, for performing Boolean set operations to combine a BSP tree with a BREP, and for determining those polygonal pieces that lie on a BSP tree's boundary. These algorithms operate on BSP trees whose nodes are each associated with a list of polygons embedded in the node's plane. Polygons are inserted into the tree using a variant of the BSP tree building algorithm. Although BSP trees provide an elegant and simple representation, polygons are subdivided as the tree is constructed and as Boolean set operations are performed, making the notation potentially less compact than other representations. By taking advantage of the BSP tree's inherent dimension independence, we can develop a closed Boolean algebra for 3D BSP trees that recursively relies on representing polygons as 2D trees, edges as 1D trees, and points as 0D trees. Boundary representations. Boundary representations, also known as B-reps. They describe an object in terms of its surface boundaries, vertices, edges, and faces. Some B-reps are restricted to planar, polygonal boundaries and may even require faces to be convex polygons or triangles. Determining what constitutes a face can be particularly difficult if curved surfaces are allowed, as shown in this figure. Curved faces are often approximated with polygons. Alternatively, they can also be represented as surface patches if the algorithms that process the representation can treat the resulting intersection curves, which will in general be of higher order than the original surfaces. B-reps grew out of the simple vector representations used in earlier chapters and are used in many current modeling systems. Many B-rep systems support only solids whose boundaries are two manifolds. By definition, every point on a two-manifold has some arbitrarily small neighborhood of points around it that can be considered topologically the same as a disk in the plane. This means that there is a continuous one-to-one correspondence between the neighborhood of points and the disk, as shown in these figures A and B. For example, if more than two faces share an edge, as in this figure C, any neighborhood of a point on that edge contains points from each of those faces. It is intuitively obvious that there is no continuous one-to-one correspondence between this neighborhood and a disk in the plane. Polyhedra and Euler's formula. A polyhedron is a solid that is bounded by a set of polygons whose edges are each a member of an even number of polygons, exactly two polygons in the case of two manifolds, and that satisfies some additional constraints. A simple polyhedron is one that can be deformed into a sphere, that is, a polyhedron that, unlike a torus, has no holes. The B-rep of a simple polyhedron satisfies Euler's formula, which expresses an invariant relationship among the number of vertices, edges, and faces of a simple polyhedron. V minus E plus F equals 2, where V is the number of vertices, E is the number of edges, and F is the number of faces. This figure shows some simple polyhedra and their number of vertices, edges, and faces. Note that the formula still applies if curved edges and non-planar faces are allowed. Euler's formula by itself states necessary but not sufficient conditions for an object to be a simple polyhedron. One can construct objects that satisfy the formula but do not bound the volume by attaching one or more dangling faces or edges to an otherwise valid solid. Additional constraints are needed to guarantee that the object is a solid. Each edge must connect two vertices and be shared by exactly two faces. At least three edges must meet at each vertex and faces must not interpenetrate. A generalization of Euler's formula applies to two manifolds that have faces with holes. V minus E plus F minus H equals 2 into C minus G, where H is the number of holes in the faces, G is the number of holes that pass through the object, and C is the number of separate components, parts of the object, as shown in this figure. If an object has a single component, its G is known as its genus. If it has multiple components, then its G is the sum of the genera of its components. Additional constraints are also needed to guarantee that the objects are solids. Baumgart introduced the notion of a set of Euler operators that operate an object satisfying Euler's formula to transform the objects into new objects by adding and removing vertices, edges, and faces. Mancilla proves that all valid B-reps can be constructed by a finite sequence of Euler operators. Other operators that do not affect the number of vertices, edges, or faces may be defined that tweak an object by moving the existing vertices. Perhaps the simplest possible B-rep is a set list of polygonal faces, each represented by a list of vertex coordinates. To represent the direction in which each polygon faces, we list the polygon's vertices in clockwise order, as seen from the exterior of the solid. To avoid replicating coordinates shared by faces, we may instead represent each vertex of a face by an index into a list of coordinates. In this representation, edges are represented implicitly by the pairs of adjacent vertices in the polygon vertex lists. Edges may instead be represented explicitly as pairs of vertices, with each face now defined as a list of indices in the list of edges, into the list of edges. The winged edge representation. Simple representation makes certain computations quite expensive. For example, discovering the two faces shared by an edge, that is, to help prove that a representation encodes a valid solid, requires searching the edge lists of all the faces. More complex B-reps have been designed to decrease the cost of these computations. One of the most popular is the winged edge data structure. Each edge in the winged edge data structure is represented by pointers to its two vertices, to the two faces sharing the edge, and to 4 of the additional edges emanating from its vertices as shown in this figure. Each vertex has a backward pointer to one of the edges emanating from it, whereas each face points to one of its edges. Note that we traverse the vertices of an edge in opposite directions when following the vertices of each of its two faces in clockwise order. Labeling the edge's vertices N and P, we refer to the face to its right when traversing the edge from N to P as its P face, and the face to its right when traversing the edge from P to N as its N face. For edge E1 in given figure, if N is V1 and P is V2, then F1 is E1's P face and F2 is its N face. The 4 edges to which each edge points can be classified as follows. The 2 edges that share the edge's N vertex are the next clockwise edge of the N face and the previous counterclockwise edge of the P face, E3 and E2 respectively. The 2 edges that share the edge's P vertex are the next clockwise edge of the P face and the previous counterclockwise edge of the N face, E4 and E5 respectively. These 4 edges are the wings from which the winged edge data structure gets its name. Note that the data structure described here handles only faces that have no holes. This limitation can be removed by representing each face as a set of edge loops, a clockwise outer loop, and 0 or more counterclockwise inner loops for its holes. Alternatively, a spatial auxiliary edge can be used to join each hole's boundary to the outer boundary. Each auxiliary edge is traversed twice, once in each direction, when a circuit of its faces' edges is completed. Since an auxiliary edge has the same face on both of its sides, it can be easily identified because its 2 face pointers point to the same face. A B-rep allows us to query which faces, edges or vertices are adjacent to each face, edge or vertex. These queries correspond to 9 kinds of adjacency relationships. The winged edge data structure makes it possible to determine in constant time which vertices or faces are associated with an edge. It takes longer to compute the other adjacency relationships. One attractive property of the winged edge is that the data structures for the edges, faces and vertices are of a small constant size. Boolean set operations. B-reps may be combined using the regularized Boolean set operators to create new B-reps. One approach is to inspect the polygons of both objects, splitting them if necessary, to ensure that the intersection of a vertex, edge or face of one object with any vertex, edge or face of another is a vertex, edge or face of both. The polygons of each object are then classified relative to the other object to determine whether they lie inside or outside or on its boundary. A polygon may be classified by the ray casting technique. Here we construct a vector in the direction of the polygon surface, normal from a point in the polygon's interior, and then find the closest polygon that intersects the vector in the other object. If no polygon is intersected, the original polygon is outside the object. If the closest intersecting polygon is coplanar with the original polygon, then this is a boundary-boundary intersection, and comparing polygon normals indicates what kind of intersection it is. Otherwise, the dot product of the two polygons normals is inspected. A positive dot product indicates that the original polygon is inside the other object, whereas a negative dot product indicates that it is outside. A zero dot product occurs if the vector is in the plane of the intersected polygon. In this case, the vector is perturbed slightly and is intersected again with the other object's polygons. Vertex adjacency information can be used to avoid the overhead of classifying each polygon in this way. If a polygon is adjacent to, that is, shares vertices with, a classified polygon and does not meet the surface of the other object, then it is assigned the same classification. All vertices on the common boundary between objects can be marked during the initial polygon splitting phase. Whether or not a polygon meets the other object's surface can be determined by checking whether or not it has boundary vertices. Each polygon's classification determines whether it is retained or discarded in the operation creating the composite object. For example, in forming the union, any polygon belonging to one object that is inside the other object is discarded. Any polygon from either object that is not inside the other is retained, except in the case of coplanar polygons. Coplanar polygons are discarded if they have opposite surface normals, and only one of a pair is retained if the directions of the surface normals are the same. Deciding which polygon to retain is important if the objects are made of different materials. Non-polyhedral B-reps. Consider the problem of representing a cylindrical object in a cylindrical hole with polyhedral B-reps as shown in this figure. If the boundaries of the actual objects touch, then even if the boundaries of the two polyhedral approximations are initially coincident as well, the approximations will intersect if one is slowly rotated, no matter how many polygons are used in the approximation. One promising approach to exact B-reps allows sculpted surfaces defined by curves, since each individual surface may not itself be closed. Thomas has developed an algorithm for alpha 1 that performs regularized Boolean set operations on objects whose boundaries are only partially specified as shown in this figure. Because B-reps tile an object's surface, they do not provide a unique representation of a solid. In addition, many B-rep-based systems handle only objects whose surfaces are two manifolds. Note that two manifolds are not closed under regularized Boolean set operations. The regularized union of two B-rep cubes positioned such that they share exactly one common edge, for example, should produce four faces sharing that common edge. Constructive solid geometry methods. In constructive solid geometry, CSG, simple primitives are combined by means of regularized Boolean set operators that are included directly in the representation. An object is stored as a tree with operators at the internal nodes and simple primitives at the leaves. To determine physical properties or to make pictures, we must be able to combine the properties of the leaves to obtain the properties of the root. The general processing strategy is a depth-first tree walk to combine nodes from the leaves up the tree. The complexity of this task depends on the representation in which the leaf objects are stored and on whether a full representation of the composite object at the tree's root must actually be produced. For example, the regularized Boolean set operation algorithms for B-reps. In some implementations, the primitives are simple solids such as cubes or spheres, ensuring that all regularized combinations are valid solids as well. In other systems, primitives include half spaces which themselves are not bounded solids. For example, a cube can be defined as the intersection of 6 half spaces, or a finite cylinder as an infinite cylinder that is capped off at the top and bottom by planar half spaces. Using half spaces introduces a validity problem since not all combinations produce solids. Half spaces are useful for operations such as slicing an object by a plane, which might otherwise be performed by using the face of another solid object. Without half spaces, extra overheads is introduced, since the regularized Boolean set operations must be performed with the full object doing the slicing, even if only a slicing face is of interest. CSG does not provide a unique representation. This can be particularly confusing in a system that lets the user manipulate the leaf objects with tweaking operators. Applying the same operation to two objects that are initially the same can yield two different results as shown here. In this figure, the objects shown in A may be defined by different CSG operations from those shown in B and C. Tweaking the top of B and C upward yields different objects shown in D and E. Nevertheless, the ability to edit models by deleting, adding, replacing, and modifying subtrees, coupled with the relatively compact form in which models are stored, have made CSG one of the dominant solid modeling representations. Octrees. Hierarchical tree structures called octrees are used to represent solid objects in some graphic systems. Medical imaging and other applications that require displays of object cross-sections commonly use octree representations. The tree structure is organized so that each node corresponds to a region of three-dimensional space. This representation for solids takes advantage of spatial coherence to reduce storage requirements for three-dimensional objects. It also provides a convenient representation for storing information about object interiors. The octree encoding procedure for a three-dimensional space is an extension of an encoding scheme for two-dimensional space called quad-tree encoding. Quad-trees are generated by successively dividing a two-dimensional region, usually a square, into quadrants. Each node in the quad-tree has 4 data elements, one for each of the quadrants in the region, as shown in the figure. If all pixels within a quadrant have the same color, a homogeneous quadrant, the corresponding data element in the node stores that color. In addition, a flag is set in the data element to indicate that the quadrant is homogeneous. Suppose all pixels in quadrant 2 of previous figure are found to be red. The color code for red is then placed in data element 2 of the node. Otherwise, the quadrant is said to be heterogeneous, and that quadrant is itself divided into quadrants. The corresponding data element in the node now flags a quadrant as heterogeneous and stores the pointer to the next node in the quad tree. An algorithm for generating a quad tree tests pixel intensity values and sets up the quad tree nodes accordingly. If each quadrant in the original space has a single color specification, the quad tree has only one node. For a heterogeneous region of space, the successive subdivisions into quadrants continues until all quadrants are homogeneous. This figure shows a quad tree representation for a region containing one area with a solid color that is different from the uniform color specified for all other areas in the region. Quad tree encodings provide considerable savings in storage when large color areas exist in a region of space, since each single color area can be represented with one node. For an area containing 2n by 2n pixels, a quad tree representation contains at most n levels. Each node in the quad tree has at most 4 immediate descendants. An octree encoding scheme divides regions of three-dimensional space, usually cubes, into octants and stores 8 data elements in each node of the tree. Individual elements of a three-dimensional space are called volume elements or voxels. When all voxels in an octant are of the same type, this type value is stored in the corresponding data element of the node. Empty regions of space are represented by voxel type void. Any heterogeneous octant is subdivided into octants, and the corresponding data element in the node points to the next node in the octree. Procedures for generating octrees are similar to those for quad trees. Voxels in each octant are tested, and octant subdivisions continue until the region of space contains only homogeneous octants. Each node in the octree can now have from 0 to 8 immediate descendants. Algorithms for generating octrees can be structured to accept definitions of objects in any form, such as a polygon mesh, curved surface patches, or solid geometry constructions. Using the minimum and maximum coordinate values of the object, we can define a box parallelepiped around the object. This region of three-dimensional space containing the object is then tested octet by octet to generate the octree representations. Once an octree representation has been established for a solid object, various manipulation routines can be applied to the solid. An algorithm for performing set operations can be applied to two octree representations for the same region of space. For a union operation, a new octree is constructed with the combined regions for each of the input objects. Similarly, intersection or difference operations are performed by looking for regions of overlap in the two octrees. The new octree is then found by either storing the octants where the two objects overlap or the region occupied by one object but not the other. Three-dimensional octree rotations are accomplished by applying the transformations to the occupied octants. Visible surface identification is carried out by searching the octants from front to back. The first object detected is visible, so that information can be transferred to a quad-tree representation for display. Primitive instancing. In primitive instancing, the modeling system defines a set of primitive 3D solid shapes that are relevant to the application area. These primitives are typically parameterized not just in terms of the transformations, but on other properties as well. For example, one primitive object may be a regular pyramid with a user-defined number of faces meeting at the apex. Primitive instances are similar to parameterized objects, except that the objects are solids. A parameterized primitive may be thought of as defining family of parts whose members vary in a few parameters, an important CAD concept known as group technology. Primitive instancing is often used for relatively complex objects such as gears or bolts that are tedious to define in terms of Boolean combinations of simpler objects, yet are readily characterized by a few high-level parameters. For example, a gear may be parameterized by its diameter or number of teeth as shown in this figure. Although we can build up a hierarchy of primitive instances, each leaf node instance is still a separately defined object. In primitive instancing, no provisions are made for combining objects to form a new higher-level object, using, for example, the regularized Boolean set operations. Thus, the only way to create a new kind of object is to write the code that defines it. Similarly, the routines that draw the objects or determine their mass properties must be written individually for each primitive. Sweep representations. Sweeping an object along a trajectory through space defines a new object called a sweep. The simplest kind of sweep is defined by a 2D area swept along a linear path normal to the plane of the area to create a volume. This is known as translational sweep or extrusion and is a natural way to represent objects made by extruding metal or plastic through a die with the desired cross-section. In these simple cases, each sweep's volume is simply the swept object's area times the length of the sweep. Simple extensions involve scaling the cross-section as it is swept to produce a tapered object, or sweeping the cross-section along a linear path that is not normal to it. Rotational sweeps are defined by rotating an area about an axis. This figure shows two objects and simple translational and rotational sweeps generated using them. The object being swept does not need to be a 2D. Sweeps of solids are useful in modeling the region swept out by a machine tool cutting head or a robot following a path as shown in this figure. Path of a cutting tool modeled as a solid sweep is used to define model of an aircraft part. Photograph of actual part that is milled from automatically generated instructions. Sweeps whose generating area or volume changes in size, shape or orientation as they are swept and that follow an arbitrary curved trajectory are called general sweeps. General sweeps of 2D cross-sections are known as generalized cylinders in computer vision and are usually modeled as parameterized 2D cross-sections swept at right angles along an arbitrary curve. General sweeps are particularly difficult to model efficiently. For example, the trajectory and object shape may make the swept object intersect itself, making the volume calculations complicated. As well, general sweeps do not always generate solids. For example, sweeping a 2D area in its plane generates another 2D area. In general, it is difficult to apply regularized Boolean set operations to sweeps without first converting to some other representation. Even simple sweeps are not closed under regularized Boolean set operations. For example, the union of two simple sweeps is in general not a simple sweep as shown in this figure. Despite problems of closure and calculation, sweeps are a natural and intuitive way to construct a variety of objects. For this reason, many solid modeling systems allow users to construct objects as sweeps, but store the objects in one of the other representations. Spatial partitioning representations. In spatial partitioning representations, a solid is decomposed into a collection of adjoining, non-intersecting solids that are more primitive than, although not necessarily of the same type as, the original solid. Primitives may vary in type, size, position, parameterization, and orientation, much like the different shaped blocks in a child's block set. How far we decompose objects depends on how primitive the solids must be in order to perform readily the operations of interest. Cell decomposition. One of the most general forms of spatial partitioning is called cell decomposition. Each cell decomposition system defines a set of primitive cells that are typically parameterized and are often curved. Cell decomposition differs from primitive instancing in that we can compose more complex objects from simple, primitive ones in a bottom-up fashion by gluing them together. The glue operation can be thought of as a restricted form of union in which the objects must not intersect. Further restrictions on gluing cells often require that no cells share a single point, edge, or face. Although cell decomposition representation of an object is unambiguous, it is not necessarily unique. Cell decompositions are also difficult to validate since each pair of cells must potentially be tested for intersection. Nevertheless, cell decomposition is an important representation for use in finite element analysis. Spatial occupancy enumeration. Spatial occupancy enumeration is a special case of cell decomposition in which the solid is decomposed into identical cells arranged in a fixed, regular grid. These cells are often called voxels, volume elements in analogy to pixels. This figure shows an object represented by spatial occupancy enumeration. The most common cell type is a cube, and the representation of space as a regular array of cubes is called a cubaril. When representing an object using spatial occupancy enumeration, we control only the presence or absence of a single cell at each position in the grid. To represent an object, we need only to decide which cells are occupied and which cells are not. The object can thus be encoded by a unique and unambiguous list of occupied cells. It is easy to find out whether a cell is inside or outside of the solid, and determining whether two objects are adjacent is simple as well. Spatial occupancy enumeration is often used in biomedical applications to represent volumetric data obtained from sources such as computerized axial tomography (CAT) scans. Spatial occupancy enumeration has a number of obvious failings that parallel those representing a 2D shape by a 1-bit deep bitmap. There is no concept of partial occupancy. Thus, many solids can only be approximated. If the cells are cubes, then the only objects that can be represented exactly are those whose faces are parallel to the cube sides and whose vertices fall exactly on the grid. Like pixels in a bitmap, cells may in principle be made as small as desired to increase the accuracy of the representation. Space becomes an important issue since up to n cubed occupied cells are needed to represent an object at a resolution of n voxels in each of the 3 dimensions. Sweep representations. Sweeping an object along a trajectory through space defines a new object called a sweep. The simplest kind of sweep is defined by a 2D area swept along a linear path normal to the plane of the area to create a volume. This is known as translational sweep or extrusion and is a natural way to represent objects made by extruding metal or plastic through a die with the desired cross-section. In these simple cases, each sweep's volume is simply the swept object's area times the length of the sweep. Simple extensions involve scaling the cross-section as it is swept to produce a tapered object or sweeping the cross-section along a linear path that is not normal to it. Rotational sweeps are defined by rotating an area about an axis. This figure shows two objects and simple translational and rotational sweeps generated using them. The object being swept does not need to be a 2D. Sweeps of solids are useful in modeling the region swept out by a machine tool cutting head or a robot following a path as shown in this figure. Path of a cutting tool modeled as a solid sweep is used to define model of an aircraft part. Photograph of actual part that is milled from automatically generated instructions. Sweeps whose generating area or volume changes in size, shape or orientation as they are swept and that follow an arbitrary curved trajectory are called general sweeps. General sweeps of 2D cross-sections are known as generalized cylinders in computer vision and are usually modeled as parameterized 2D cross-sections swept at right angles along an arbitrary curve. General sweeps are particularly difficult to model efficiently. For example, the trajectory and object shape may make the swept object intersect itself, making the volume calculations complicated. As well, general sweeps do not always generate solids. For example, sweeping a 2D area in its plane generates another 2D area. In general, it is difficult to apply regularized Boolean set operations to sweeps without first converting to some other representation. Even simple sweeps are not closed under regularized Boolean set operations. For example, the union of two simple sweeps is in general not a simple sweep as shown in this figure. Despite problems of closure and calculation, sweeps are a natural and intuitive way to construct a variety of objects. For this reason, many solid modeling systems allow users to construct objects as sweeps but store the objects in one of the other representations. Conclusion. In this chapter we have covered the following in detail: representation of solids, primitive instancing, sweep representations, boundary representations, spatial partitioning representations, constructive solid geometry methods, octrees, binary space partitioning trees.